All right, so this is going to be part 3 of this limit homework, kind of intro to limits. And we've got a trig function here, so let's check out this trig function. So we're going to, whenever we're doing limits, let's always just kind of think of this as a function first, unless it's piecewise. If it's a piecewise function, then you really kind of have to look at each piece, and there might be a piecewise coming up, we'll see. But otherwise, just consider it a function and just attempt to plug it in and see what happens. So let's try to plug a 0 into this. All right, so I'm just plugging in a 0. We are going to have some trig functions here with 0. So remember, this is 0 and pi over 2 and pi and 3 pi over 2. And this is on a unit circle, so the radius is 1 here. Oh, that was really bad of me. 1. 1. Negative 1. Negative 1. So anyway, the point here would be the point 1, 0. And recall, this is cosine sine. So this is going to be 2 plus 0 plus, well, the sine of 0 is also 0, over 5 times the cosine of 0, which is 1, and that gives me 2/5. So no craziness going on here. The answer is going to be 2/5. If the denominator had been 0, so if we had been approaching, say, pi over 2, we would have had a bit of a problem and would have had to look into things. But let's look at the next one. All right, so in this one, they're giving me some particular limits, and we have to find the following. So this is going to be using our laws of limits, or limit laws, and there are a list of those, but essentially, knowing these pieces, and I'll just kind of show you what's going to actually happen here. So we have the limit as x approaches 8 of f of x times g of x. So there is a limit law that says that this is the same thing as the limit as x approaches 8 of f of x times the limit as x approaches 8 of g of x. So this is a limit law. It's actually part of a theorem. And so now if you look up here, they told me that as you approach 8 of f of x, it's 4. And that if you approach 8 of g of x, you get a negative 1. So this answer must be negative 4. All right, let's look at the next one. The next one says the limit as x approaches 8, and it has 8 times f of x times g of x. So first, we can use that multiplication property that we just used a minute ago that says we can break this up. So this is the limit as x approaches 8 of 8 times the limit as x approaches 8 of f of x times the limit as x approaches 8, g of x. All right, so then we can just kind of look at these pieces. So the first one is the limit of a constant. Notice that this is just a constant. If you think about the graph of that, it's a horizontal line, right? At 8. It's just a horizontal line. So no matter what you approach on the x-axis, your y value, your function will always be 8. So that first part is actually equal to 8. And that's the rule of constants. All right. For the second one, the limit for the f of x, we know that that's equal to 4, and the limit for the g of x we know is equal to negative 1, so our answer here is going to be negative 32. All right, let's look at C. This one has the limit as x approaches 8, f of x plus 7 g of x. All right, so same kind of deal. We can, just like we had a multiplication property, we also have an addition property. So we can break this up using the addition property. All right, then we can break that second one up even further using the multiplication property. All right, so then we use sworn my eraser was much bigger than that. And so then we know that this one is a 4. Here's a constant, so we know he's 7. You see, no matter where you go, on the line 7, here's the line 7, no matter what x you approach, this will always be at 7. So 7, and then times your -1, so that's 4 minus 7, which is -3. And the more you get a hang of kind of using these rules, the easier things will be. That kind of sounded like a threat. I didn't mean that to sound like a threat. Okay, so let's look at the last one and see what properties it entails. So we have the limit as x approaches 8, f of x divided by f of x minus g of x. All right, so the first thing we can do is we can break up this division as long as that denominator is not 0. So let's go ahead and break this up. All right, and now on the bottom, so that was a division property right there. And then I can also use the subtraction property down here, which is really the addition property with a negative, to split that one up. Now again, hopefully that denominator is not 0, so now we can just kind of plug the pieces in. That first one is a 4. That one's a 4, and that one is a -1. Notice that is not 0. And we get 4/5. So just using all of our properties, or limit laws, the laws of limits. All right, let's check out number 13. 13 is using the same rules again, so you can just kind of play with those. This one does have 3. So just go through your rules here and just make sure in your mind you're going, okay, I just used the addition property. I used the constant property, because these can come up again worded differently. So just this one is all about those limit laws again. All right, so let's look at number 14. All right, so in this one it says, because of their connection with secant lines, tangents, and instantaneous rates, limits of this form occur frequently. And we actually had one similar to this in the earlier homework, and I mentioned that being the difference quotient, you know, with h approaching 0. This is the definition of the derivative, right? This is the slope of the tangent line to the curve f of x at the point x, y, whatever. So we actually have seen this before. Anyway, so it says evaluate this limit for the given value of x and function f. All right, so you can do this in pieces. Sometimes that helps. So if you just want to kind of look at, let's see what f of x plus h is going to look like. So remember, that means we're going to plug this entire x plus h into that little x right there. So this is the square root of, oh, that wasn't very exciting, x plus h. Sometimes these are really long. That was not. And so then we're going to subtract off f of x. So that's going to look like this, so minus the square root of x. And then we're going to be dividing that by h. So let's just go ahead and put this together because that wasn't as exciting as I thought it was going to be. So here's f of x plus h minus f of x all divided by h. Now notice if you tried to plug the h in right now, or yeah, well, if you tried to plug that 0 in right now, you would get 0 over 0, which is no good, but when you see 0 over 0, that means you can play with it. So what we're going to do is we're going to multiply by, we see those square roots, we're going to multiply by his conjugate, top and bottom. So you guys are used to thinking about multiplying by conjugates of denominators, but you can actually do either one, because remember, essentially, you're just multiplying by the number 1, which is what that number is right there. So let's see what happens here as we simplify this. Multiplying by conjugates, remember, all that does is square the first one minus square the second one, right? It's a difference of squares. And then on the bottom, I'm not going to multiply that out. If I do, I'll just have to undo it in a second. So it's going to look like that. I'm going to go ahead and erase that part. All right, so on the top, we're going to have x plus h minus x. If you have a square root and square it, you end up with that radicand, the thing underneath. And then on the bottom, we're going to have an h over here, x plus h plus square root of x. Notice on top, that's just an h. And now those h's divide out. Keep in mind, they're dividing out, not canceling. There's a 1 on top there still. Oh, I made that very big. So now it looks like this. Let's try plugging the h in again. So let's evaluate this when h is 0. That's just notation for saying I'm about to look at this when h is 0. So let's plug the 0 back in for h. And we get 1 over the square root of x plus 0 plus the square root of x, which is 1 over 2 square roots of x. So this would be the answer kind of in general, but then they actually gave me a particular x to plug in. So look back up here. They want me to look at this when x is 14. So let's plug in. So here I go again. That notation. Let's look at this when x is 14. So 1 over 2 times the square root of 14. There's really nothing. I mean, I guess we could rationalize it, but I think that's a fine answer if you want to leave it like that. If you do rationalize, it will look like this. So there it is, rationalized. And so again, what we just did, this is the slope of the tangent line to the curve f of x at the point x, okay? So in this case, at x equals 14. Now, another word for that is the derivative, which we won't know just yet, but we will find out soon enough. So let's look at this last one. And here they want me to, let's see, it says, oh, this is kind of a cool one. So this is using the sandwich theorem is what it's called. So what the sandwich theorem says in a nutshell is that if you've got some function f of x, ooh, I did not mean for the highlighter to be on. So let's say you have some function, well, they called theirs f of x, but pay no attention to that. Let's say you've got some function f of x who is always greater than or equal to some function g of x. So I don't know what this one looks like. I don't know what this one looks like, but f of x is always greater than or equal to g of x. So then let's say you come along with yours, and yours is, I don't know, let's say h of x, and it turns out that yours is between those two, or less than or equal to, actually. So your function is sandwiched between these two. So if f of x has a limit of L as we approach some value, and g of x also has that limit of L as he approaches some value, that means that no matter what your guy is doing, he has got to have the same limit. So if you are sandwiched, oops, that was supposed to be the yellow highlighter. If you are sandwiched between two functions and you know that they have the same limit, he goes to L, he goes to L, you're stuck in between them, then you must also go to L. So it's actually a pretty cool thing. So this one says that our function that we're looking at, f of x, it says he is always between 10 minus x squared and 10 minus 7x squared. So he's always there when x is between 1 and -1. He will always be between those two values. So then it says, so what happens to our function as x goes to 0? So I want x heading to 0. Well, at 0, 0's in between here, right? So when he goes to 0, and the 0 is always in between these two things, then we can check out what happens to him as he goes to 0 and what happens to him as he goes to 0. So let's just see. What happens to this guy as x goes to 0? Well, he goes to the square root of 10, doesn't he? Just plug a 0 in right there. What happens to this guy when x goes to 0? Well, he also goes to the square root of 10. So the 0 is in between the -1 and 1. F of x is always in between those two if we're between -1 and 1. Therefore, our guy must also go to the square root of 10. He goes to the square root of 10, he goes to the square root of 10. I'm stuck in between, so I must also go to this, whoa, I'm not finding a good marker, to the square root of 10. So this is called the sandwich theorem, and tells me my answer. So pretty cool. I always forget how to spell sandwich. Sandwich? There. So anyway, and that's it.